Okay, so last time we were talking about speech APIs, speech to text, text to speech, because this week we are looking at multimodal. So today we are going to look at image generation and image recognition. Interestingly, we actually started off with image recognition first in terms of the history or the sequence by which the technology developed. The first technology that first developed was image recognition, starting off with what we call optical character recognition, which is the ability for computers to be able to recognize written characters, people's handwritings, or scanned documents, and all of that. So we started off with that. Um, and then later on, we had this whole new array of different kinds of technologies that allowed computers to generate images that looked very realistic. So we are going to look at some of those. We'll look at some of the models that are available for us so that we can, do interesting things with images, basically to generate these images and we'll look at how we can write really good prompts. Writing prompts for images is quite interesting and it's not straightforward because in most cases, um, if you are generating an image, just a small change or difference in your prompts can result in a totally different image. So one of the things that you will learn is how we can write really good prompts that will help us to be able to generate images that more or less match our requirements. It's actually a very tricky thing to do, right? It's quite tricky, and we're going to do a bit of hands-on just to see, what that means, right? Or how we can work around some of that trickiness. So, we are going to look at fundamentals of image generation. We're going to try to understand some of the technology behind it, right? Understanding the technology helps us because we understand the limitations of some of you know, uh, these models and how we can work around those limitations. So just the same way we're talking about LLMs in general, right? This same thing also applies to image generation models and image recognition models. Then we're going to look at some APIs. There are a lot of AI service providers that will provide some really nice models as well that can do all of this, right? But at the same time, um, we have to remember that um, in cases where these models, the API is not available, we can run them locally. So how can we, achieve or obtain the same results, by doing that? So then we are going to look at OCR. OCR is basically optical character recognition. So like I said before, OCR is a very old technology that existed even before we had these latest, machine learning models, especially the ones that are based on neural networks and so on, right? We had OCR that was built using vector graphics and a bunch of other different technologies, there's a very powerful and popular library called CV, which is typically used, for optical character recognition. And they use things what we call polygons, basically, to be able to manage, some of the things that for it to achieve some of the things that it achieves. So it's something that we're going to look at. But the interesting thing is that you can combine it as well with the neural network based models that we have currently that have become very mature and very good at being able to predict or being able to generate or predict basically text or recognize text based on scanned images. So yeah, then at the end we'll also see how we can build applications by combining all of these multimodal features, models, and combining text, image, and audio models, maybe with a few code examples in Python, which we can also extend to other things. So let's start off with image generation. So in image generation, first of all, image generation is a process of creating synthetic images using machine learning models that understand the patterns in visual data. So effectively, you have trained these models on visual data, and then after training them, you can then ask them, just like with text generation, you can actually ask them to generate images for you, and they will do a great job of generating these images for you. And this has become very prevalent. Of course, almost everyone here, you have seen AI generated images. And of course, we have even gone beyond generating images to generating videos, animations, and all kinds of things, style transfers, all kinds of things, right? So this is very powerful, and it, we are going to try it, right, and learn how to manipulate images. Both we're going to use code in our own example because we want to, as developers, we want to see how you can build such tools. So there are several classes of image generators. You have what we call diffusion models. Then we have transformer-based generators. And then we have autoregressive or the older methods using GAN-based models, right? So then we're also going to talk about control net and guided generation. And then we're going to look at some of the prompt engineering fundamentals. Some of the things you need to know about the prompts that you use for image generation, including content style and the constraints. So when we talk about the classes of image generators, you have what we call diffusion models. The diffusion models are the most common approaches that are used today, right? And typically what they do is that they start with a canvas that is basically noisy, a noisy canvas. So what I mean by a noise, when in the context of video or image, if you think about when you put on a television and there is no signal, you get this sound, and then what you see on the screen is, a what we call white noise, right? That's a noisy. So that is the kind of image you would get if you start off um you know with a an array, because images are basically an array of four-dimensional numbers, right? Or a matrix of four-dimensional numbers. The four dimensions represent the colors of each pixel. The first three is the RGB, the red, the green, the blue. And then the fourth is the alpha. Alpha in this context means the transparency, right? Or opacity of that pixel. So by the time you take this RGBA, which is represented by four floating point numbers in a vector, and you take this and you form a matrix of it. Of course, the matrix now forms the pixels, on a row by row basis, right? So that is basically taken and rendered on your screen and forms an image. Now, but if those numbers are just random numbers that are generated anyhow, what you get is that noisy, thing that gets displayed rather on a screen. So the diffusion model is a model that was trained on such data. And we're going to talk about how that training happens. So because it was trained on such data, it actually learns how to gradually remove the noise from that data and come up with an image. So it's kind of I think of it like a subtractive process. You know, a sculptor takes a flat piece um, you know, um, of iron or concrete or whatever and begins to remove parts of it gradually until a sculpture comes out of it. That is kind of like, how stable diffusion or how diffusion models rather work. So stable diffusion is, one of the um, foremost or most popular, image generation models that uses this diffusion approach, right? So you have other ones, you have Midjourney, you have SDXL, right? So the beauty of these diffusion models is that you have a lot of control over what it generates or how it generates it, right? So there's a high control factor, strong detail. It can come up with a lot of really great detail, right? And then there are open source options. So there are a lot of diffusion models in the open source that have been open source that you can basically access. Hugging Face is another good place where you can see a lot of image generation models. So that's the first category. The second is the transformer-based generators. So a transformer is the latest neural network technology that is based on what we call an attention mechanism, right? So these ones, you basically are training a model to use what we call sequence modeling on pixels and patches, right? And then you use that sequence model to basically generate images. So examples of transformer-based generators would be DALL-E. DALL-E um, is a model that was created. I think it's one of the early models, right? That was created, and it is um it's the first. It's owned by OpenAI, right? OpenAI is they kind of started that whole idea, and that that method has also been used by many others, including imaging and so on. So you see a lot of different other image generation models that use this transformer-based approach. So the one of the advantages of using a transformer-based generator is that it has a more semantic understanding. In other words, it can interpret your text into an image much better because it's using a sequence model. Transformers, LLMs, large language models are actually based on transformers. So it's a sequence model. What we mean by sequence model in machine learning is a model that you give a sequence of information and it's able to make meaning out of the sequence. The sequence matters. That's why it's used for natural language processing. That's why it's used for large language models. So since that's how it is used, to also generate images, it does mean that the images will also kind of have an understanding of the sequential nature of text, for example. So that is the second type. Then the third kind of image generators are the GANs. So the GAN is a generative um, adversarial network. It's a generative adversarial network. So that name, generative adversarial, is based on the technology that is used to train it, right? So it's basically two networks. One is a generative network, the other one is an adversarial network. So the idea is that the generative network tries to generate an image, while the adversarial network tries to um, basically, how do I put it now? Um, it tries to let's say knock down. Let me use that terminology. The image that the generative network is creating. And when I say knock down, I don't mean destroy it, right? But what I mean is the idea is that you are training a model and you are telling it generate an image that a human being will not be able to differentiate from a real image. So you are trying to you know the 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 training target or the objective for the network is that a human being should not be able to know that this image was generated. So the adversarial network, its own job is to detect that this image was generated. So the better is able to detect it, the better the more the generator tries to um generate a better image so that the discriminator, the adversarial network is actually a discriminator, tries to do the opposite. So they are basically kind of fighting each other. The generator is trying to do a perfect job in generating, while the discriminator is doing a perfect job in identifying or discriminating, identifying that it is generated. So they both learn and get better and better until the generator becomes really good at generating images that look very human. The GANs were actually the first really good image generators, right? They were the first really good ones. But these days, nobody really uses GANs, right? Because the diffusion models have become much better, and you have better control, you know, over the details of what the diffusion model is generating versus, if you are just using these other ones, the GANs or the transformer based, you can even see control transformer based generators, but the GANs, you don't really have very good control, right? But they are still used, for specialized tasks. So those are the different types of image. So let's talk a little bit about the generation overview. So the GAN, which is the first type, like I said, is a class of deep learning models used for generating realistic new images that resemble a training data set. So the core idea, which was proposed by Ian Goodfellow in 2014, involves a competitive adversarial process between two neural networks, a generator and a discriminator. So the process is often compared to a game between a forger, which is the generator, and a detective, the discriminator. So that's what I was kind of trying to explain. So the generator creates new synthetic images starting from random noise. It always starts from random noise. And its goal is to produce images that are convincing enough that the discriminator cannot differentiate those generated images from real images, right? So, and of course, the differentiator, which is really good, cannot, then a human being cannot as well, or discriminator rather. So, um, so that's the whole idea, convincing enough to be mistaken for real images. The discriminator is then trained on a data set of both real images and the fake images that come from the generator. And its task is to classify whether the images that come, whether it's real or fake. So the adversarial process involves both networks improving through competition. So the generator gets feedback on how to create more realistic images when its fakes are detected by the discriminator. So the discriminator also gets better at spotting even the most subtle differences that between the generator's images and the real images. So you have the two of them continuously put in this process of competing. The generator generates, the discriminator discriminates. And because the generator wants to improve its score against the discriminator, it becomes better at generating. And because the discriminator also wants to improve its score against the generator, it becomes better at discriminating. And because getting better at discriminating, the generator is going to be forced to also get even better at generating. So at the end of the day, we get to a point where the generated images are nearly indistinguishable from real ones. I think the main challenge that you see with the GAN approach is that it takes a lot of compute because of this whole process of competition. You're essentially training two networks, two neural networks. You're training a generator, you're training a discriminator, and that takes twice the amount of time. So I think that's one of the biggest challenges. Then the second method is the image diffusion. So if you looked at this when I came into this slide, you see that you started from a noisy image. So that first thing that you see there is the noise, right? Then over time, the diffusion model begins to learn, like you can see here, and begins to remove, noise from the noisy image until an actual image crystallizes out. And that's the process of diffusion. So the image diffusion method is an AI technique generating realistic images by learning to reverse a process of adding noise to data, right? So essentially, you're turning the pure static, which you have the pure static there, back into a meaningful picture. So the diffusion process or approach is what is used for stable diffusion and DALI, like I mentioned, and it works in two stages. So you have a forward process where the noise is gradually added to an image until it's unrecognizable, and then you have a reverse process where you train a model to reverse what was done during the forward process. So the model learns to gradually remove that noise, starting from random noise to create new novel high quality images from text prompts or other inputs. So the process, like I've described already, if you look at it, the forward process, which is called a noising, is that you take a clear image, like the image of this cat or a dog or any other image, and you slowly add noise to it gradually, right? As you're adding noise to it, you're actually taking um, checkpoints of it, right? You are keeping track of the image as you're adding noise to it. So that's the fourth step, right? And you do that over many steps. So eventually at the end of the day, by adding a lot of noise, it becomes this noisy image that doesn't contain anything, right? Then in the reverse diffusion process, what we call the denoising process or the generation, phase, you now use this data to train a neural network so that it can reverse this process of noise. So if essentially the data that you created when you were noising the image, you use that to train a model. So the model learns how to denoise the image from the data that you provided. Then once you have trained that model, it learns how to denoise. So you can then give that model a new image, or basically you give that model a new um, random noisy canvas that has nothing on it, right? And of course, since you are trained it on denoising, then you can then repeatedly apply that process. It learns to denoise, right, with the random noise image, or this is basically an image that is basically random noise, right? And the model begins to learn how to remove the noise, to denoise it, and you can then give it text prompt. So as you give it the text prompt, it is denoising it guided by the text prompt. Because when you were training it, you were also giving it text prompts or text captions when you were training it. So it actually learns how to associate the text prompt with a denoising process that will arrive at an image that matches your text prompt, right? So that text prompt shapes the output until you have a coherent image, coming out from that. So this is the process for anyone who has ever wondered, how do we even get to a point where I can type a prompt and images are generated to match that prompt? This is the magic behind it. This is how those models are trained. So you see here sample code, and we're going to run some of the sample code to be able to do it. I think we did it earlier sometime. I can't remember if it was in this class. Um, but we've done it where we were able to generate some images. But we're going to go into detail this time around. The idea being that we want to learn how to properly construct our prompt so that we get images that we want. So stable diffusion does have a whole bunch of, you know, um, you can use touch to run it, right? Or if you use something like Hugging Face, you can also with Hugging Face, you don't need to use touch. You can just use their AI endpoints to call it. But this is anyway, if you're using touch, it basically means that you are running the model locally on your computer or something. But we will use the API hosted ones to run these prompts. So some of the key concepts to remember So when you say generative model, a generative model is an AI, a type of AI that is designed to generate new stuff, right? New data, whether it is images, whether it is words and sentences, whether it is speech, right? It generates stuff. That's why it's called a generative model. And then, of course, in the concept or in the context of image diffusion, this is inspired by physics, right? Because in physics, there is something we call diffusion, physical diffusion, where particles spread out. But in this case, we are doing diffusion in the opposite direction, right? We are pushing particles in until they basically make the image noisy. So some of the applications of image diffusion, text to image generation, like we said, you can put a prompt and you have image coming out from it. Then for image editing as well, what we call in painting. Then, so in those days with Photoshop, for example, you couldn't really edit images that Photoshop they did it. They've done so well, in those days. Not no. Now, Photoshop is bad. It's badass. Like you can do a lot of things. So you can only take images now, and with diffusion models, you can write text prompts to modify or edit those images, what we call in painting, right? And diffusion models are really good at that. Then you have super resolution. So have you ever had a situation where you had an image and the image wasn't sharp? And you want to improve the sharpness of the image, you want to increase the resolution, maybe it's a small image. You can do that. It is actually a generative process. It's not as if it's doing anything with that image, but it is taking that image that you already have, that blurred, unsharp image, as a prompt, as a kind of prompt, as a kind of input, and then it is using it to regenerate a sharper version of that same image. Then, of course, diffusion models have become state of the art, right? They have become dominant for image generation. Like I say, in the old days, GANs were the best, right? GANs were superb, right? But GANs now, generative adversarial networks, you can see that diffusion models have become better than GANs in terms of the quality of the images and the stability, of the images that have been generated. So when we are now talking image generation, there are some important parameters that you need to remember. So of course, a prompt, which we already know. The prompt, when you are prompting, you need to ensure that you give enough information. The information is made up of three main parts. The first one is you have to describe the content of the image, right? What should be in the image. You have to describe the style of the image, how it should look like. Whether you're making like a cartoony kind of image or whether you're just making it, like realistic or you're making it like, there are different words that we can use to describe the style of the image. Then the composition is how components of that image are placed, right? You know, things like focus, things like, okay, are you zooming in on this? Are you focusing only on the foreground? Are you blurring, out of focus the background? Those additional photographic elements that you will use, or the positional elements, relative positioning of the components of the image. These are very important because if you're not able to specify these things, what will happen is the model will basically choose whatever it likes, and you may not like that. So an example of a prompt that contains these components would be a watercolor painting. So when you say watercolor painting, you've already specified the style. The style means it is a watercolor painting of a red dragon flying over mountains. So a red dragon flying over mountains, that is the content, which is the thing that you actually want it to paint or to generate. Then you now add compositional elements, misty atmosphere. That's a compositional element. Soft lighting, that's a compositional element. So when you now add all of this together, you have a prompt that is really good and will give you a good outcome. So that's one. Then We have what we call a negative prompt. Negative prompt is when you are telling the model to be more specific, things that it should also avoid. So it is not enough to just say, oh, this or that, but you should also be able to say, don't do this or don't do that, right? It is very important. So you have to add, examples of the things that you don't want when you are talking about prompting. So you have to include the negative prompts. So a good example of this is when you say blurry and low contrast, you can say, I don't want, it shouldn't be blurry or it should be blurry, right? Or, I don't want, it shouldn't have distorted faces or it should have distorted faces, extra limbs. So those are just additional information. Then we have what we call a guidance scale, right? A guidance scale controls how strongly the model follows your prompt. Okay. So a higher value of guidance scale means it should follow your prompt more literally, more or less like exact, right? But it should be less creative. That's a higher value. But a lower value means it should be more creative and can interpret your prompt in other ways, right? It doesn't need to be exact, literal, um, um, you know, interpretations. So that can be similar to temperature. When we were doing other kinds of stuff, we use temperature to say, okay, if temperature is low, that means do more of what I want, right? If temperature is high, be more creative. But in this case, the guidance scale is kind of the opposite, right? If it is high, means do more of exactly what I have written. But if it is low, it means um, be more creative, especially interpreting the things that I have specified. So typical values are in the range of 7 to 12. Then, you also have inference steps. So inference steps, if you add more inference steps, you have more details, but it also means more computation. Because remember, the diffusion process or even the GAN generation process is done in cycles or in steps, well, epochs, if you call it. The more epochs, the more it generates, the better the generation becomes. So just like when you're training a model, the more epochs you train, the lower the loss, the better it gets at what you're trying to train it. So if you want better detail, you can specify more steps, but remember that will also mean more computation, right? So more computation, depending on how good your model is, more computation can take more time, right? In fact, it will take more time. How big your model is, how much compute you have. So if you have more compute, of course, you can do more steps because each step will take less time. So the common values for inference steps is typically 20 to 50 steps. Then we have image resolution. So image resolution would be if you are generating an image, right? What resolution do I want? Larger resolution will also take longer because large resolution is more pixels, right? So the model is going to take longer. Smaller resolution will do it faster. Also, it, some models they have limits. Of course, there is limit to what resolution models can go to, right? So if you are like with stable diffusion version 1.5, it can do up to 512 by 512 pixels, right? But if you want more, like 1024 by 1024 or 2048 by 2048, then SDXL can give you that. So higher resolutions need tiling or upscalers. What this means basically is above this 2048 by 2048, if you want much more resolution, tiling means you are essentially generating smaller sections of the image at a time. Smaller sections or tiles, what we call tiles. So you are just generating smaller sections. And tiling is a bit complicated because it has to know where it stopped and where it continues to avoid discontinuity at the point of joining the tiles, right? That's one. Upscaler is basically, after generating it at a lower resolution, you use an upscaler to essentially regenerate higher resolution versions of it. Again, maybe by using tiling or other mechanisms. Sometimes the context window of the model may not be enough for it to generate um, the entire large resolution image at once. So it has to now go, um, you know, in pieces, piece by piece. So this is an example of a prompt that you would give a Japanese garden in autumn cinematic lighting. So you can still see that content and composition. There's no style here, so it could decide to take realistic. Then you have a negative prompt that says blurry or oversaturated, which is additional negative prompt is what the model should avoid. Okay, so when you say blurry oversaturated, that means you're telling the model don't do blurry and don't do oversaturated. Then you can see the number of inference steps there. You can see the guidance scale, like we said, that is to show how much it should follow my guidance or not. Then the the dimension of the image, the height and the width, right? So we'll try this. Now, one of the things we will also try is when you change your prompt just slightly, we'll see how it impacts the image, right? And we can also do a we'll also do a live comparison of the same prompt, right? But you use different guidance scales and see how when you give the model more freedom to do more stuff with your prompt, what does it do? How does it do it? So we're going to do that a bit when we go into the hands-on. So, yeah, so what are the practical applications of image generation? So the first one is mostly, of course, creative visual assets, right? So if you are building apps, um, you need to set up your ads or banners or posters. This is a very good skill for you to have as a developer because sometimes, yes, there are all those stock images that you go and pull from somewhere, especially if you're a front-end developer, a mobile developer. There are all those stock images, banners, posters, but sometimes you may not find the exact one you want. If you have mastered the art of prompting or prompt engineering, um, an image generation model, that is additional, resource for you that you can basically generate whatever you need, right? Social media graphics, book illustrations, right? And then even for product and UI design, you could actually prompt these, you know, image generators to design mockups for you and prototypes. So the interesting thing is you can actually build a workflow for yourself where I can use an image generation model, a diffusion model or something to create mockups and prototypes for me. And then I can take that and throw it into another model that I will ask it to generate the HTML, the code, HTML or whatever markup for those images, right? So you've empowered yourself basically to be able to build end to end. Then alternative UI concepts, right? Then fast ideation, if you really need to get to quick ideation and you don't really want to bring in designers yet because you're still in ideation mode, you want to test it out. Once it is good, yes, you bring in the designers. You are not a designer actually, so unless there are some of us who are developers and have a little bit of design skills as well, then this even makes it better for you. So that's the second thing. Then synthetic data for training models. So there may be some rare edge cases that you want to use to train models. For example, damaged equipment, unusual weather. So you can use image generation to do that. You can also use it to expand data sets that you want to use for training models. You can also use it for reducing bias by balancing the class distribution of data types. Now, this is something that mostly machine learning engineers will understand. But if you have a data set that you want to train a model on, and you find that a lot of that data is only of one type or of one class, right? Then you may have a difficulty training the model because you don't have enough data for the other type. So you can generate it. So that's the benefit of that. Then the other use would be in simulation and in virtual environments. So for example, if you are building an application for, computer vision for robotics or something, you can generate images to do that. Drone navigation environments, you can also use image generation for that. Interior layout simulation, you can also use it for that. Automation and business use cases, auto-generating blog images. So, people can write blogs, right, and post. And you can call an image generator to generate a to generate an image that kind of matches um, the subject matter of that blog. You can even use a blog post or parts of it as the prompt and you generate image. Automated thumbnails. So this is where it becomes very useful for developers. If you are building stuff, you can have automated thumbnails that come from either text or elsewhere. Report summaries, image diagrams, and personalized content at scale. So there are a lot of different applications of image generation. So we are going to try a bunch of things, right? I'm just going to I'm still going to use Python in a Jupyter notebook, and I'll try a bunch of models. I'll try Gemini models. I'll try Hugging Face models. I will not try OpenAI because I do not have a paid OpenAI um, API key. So let's just get to it and see what. So first of all, I'm just going to create a new notebook. So I will first of all, um, let's see. I'll try a few models. I'm going to go to Hugging Face and see if I can get a few models, image generation. I'll also try Gemini because Gemini is a multimodal model. So it will be able to. So let me import Google generative AI as Gen AI. Let me import. So for Hugging Face, um, you you can use their inference client. So I'm going to go use their inference client. But let's do Google first. So gen AI dot pi key. So os dot get Gemini API key. Okay. Generative. I think I missed something. I need to also import OS and .env. Okay. I don't have a .env file here. That's why load.env is giving me false. So let me create a .env file. .env. Then I'm just going to go copy my keys and put. So I have my Gemini API key. I have OpenRouter. I have Hugging Face. OpenAI. I have Grok. I have Pinecone is still there. Okay, so yeah. So this is the first step. Let's run this again just to load. Then okay. Now we will go ahead to um So I will need to first of all create. Well, they have a Vertex AI. Uh, okay, let me check for Hugging Face. Um, Models. So we will have text to image. So we're looking for text to image. There is image to image as well, which is quite interesting, right? But let's go with text to image first. Um, I don't know which of these. Yeah, let's go with Quen image, right? So Quen image. Um, let's see. Um, from what I can see here, it's easy to use it, right? So of course, if you want to check sample code on Google Colab, you can just click on this and it's going to create a collab for you. I think they already have collab, right? So you use you this means you have to install it. Um, you have to install this locally, and this requires a GPU. You actually require a GPU for that. So but I want to use the AI, the API. I want to use the API. This is still the same thing. It's still requiring that you install it locally. Maybe we'll try that later on. Um, so um for Google, let's go back to Google. So for Google, um, we create a gen AI model. So model equals gen AI dot generative model. So we create a generative model and we will specify the model. So for now, let's just use our Gemini 2.5 um, Flash. I think we should be able to use that. Um, Model name. So it should be model name. Okay. All right. So once we do that, then we can create a prompt. So let's just try a simple prompt. Prompt is generate an image of an African lady. Then we run the prompt model dot generate images. Prompt generate content. So generate content is for text. Um, okay, let's let's use a newer approach. I think this is an old approach. So we create a client and then we get a model, Gemini 2.5 Flash image. Uh, um, gener Gen AI dot generative config generation config modalities. Um, then then model equals gen AI dot generative model. Specify the model name. Um, Gemini 2.5 Flash image. Well, I would really just do um response mime type. Okay, let's change this. Yeah, um, image PNG. Okay, okay. So I should specify the API key, um, Gen AI configure. So I'm seeing a lot of different approaches in their documentation. All right, so um, I don't have access to this. So let's just go with the regular Flash. Hmm. I did do this some time ago with Hugging Face. So it's actually responding with asking for more information. Um, okay, let's try something simple of an apple. I don't know why it would be asking me for so much of this additional um okay. Um so I forgot to get the response. Then when I get the response, I should save it. Um, okay, so let me bring up so let me bring up a notebook. I had already done this. Okay, so I'm going to try this, but this requires if you check the docs for Hugging Face, you see how you can also do text to image. Well, we can try this. Um, yes. So this is if you want to do Hugging Face, this is what we did the last time. So you get an image which you can save. So let's try this also. Um, I don't want to do local inference using the local inference means you have to have a GPU. While you can actually try this right on your um with your collab by selecting a GPU like a T4 or any of this, right? But I like to save it for something else. So you could do the remote inference, which is what we have here. So let's see, basically call the inference client on Hugging Face, and then you use a text to image. So let's try that approach. I'm going to come back to um, solving this, the Google one. So give me a second. Um, so I have already my Hugging Face API token here, which I get from os.environ. Provider auto. So you create a new inference client. Um, you import OS, which I've already done. And then you just call text to image. So, and then we use the Qwen image. Let's see if this works. So, I don't have this. This is not available. So let's look for a model that is free on text to image models. Let's look for free models, free. So, well, let's just try one of these. Okay, this is going to be in the, yeah, this is not going to be, is in a gated community. So, diffusers, uh, okay. So this is diffuser and so it says it's free, no payment needed. So let me just Winboy Freetown one. Let's try that. Of course, this gives me a PIL image. Because it's a PIL image, we need to write it to a file though. Okay, so I'm going to go look for something we can use. Now, this is we still need PIL because all of the image generation will generate an image that you have to write. So this is um, when I have finished generating from Google, this is from Gemini. When I have finished generating, I have the uh, results. We have candidates, you have model version, but you need to get the content. So the content is a binary file which actually contains the image, right? So you have candidate content parts. So you go through each of the parts and then you run image data, path.blob data, mime type. Then you open the image using PIL, which is a Python class for managing and manipulating images. Then you basically save the image into this path, right? And then um, with that, we can actually go and check. It will save it here. So let me run this. We should have the image here if it was successful. Okay, so Gemini 2.5 Flash didn't actually give me um, an image. Okay, so I'm going to come back to this. Let me complete the second part of it. I'm going to come back to this with the code that actually works in generating images and pulling it. So, but let's continue. Okay, so so beyond image generation, the next thing when you're manipulating images is image recognition, right? So with image recognition, you basically are giving your model an image and you are asking your model to either do something with that image. For example, identify faces of people, identify objects, right? Or classify what the image, contains, or caption, things that are in that image. So these are some of the tasks that you will do with image recognition. You have image classification, which is assign a label. So examples of the um, these are examples of APIs that will provide you image classification models, OpenAI, Google Vision, and Hugging Face Vit. Then you also have object detection. Object detection is where you want to be able to detect what are the objects in an image, right? So for example, if you have people or animals or balls or cars, whatever, right? So it detects the objects and it does what we call bounding boxes. A bounding box is basically a box that is drawn around an object to show the boundary of that object. And it's typically drawn as a rectangle or something. So these are the models that will give you that functionality. You have the AWS recognition, and then you have the YOLO models. YOLO means you only live once, but a it is also um, I would consider them a service provider, right? That basically they train a lot of models for computer vision, image recognition, object detection, all those kind of stuff. Then we have image captioning. So this is also another thing you want to do where you have images and you want to give good captions to the images, right? So that's image captioning. Then you have, of course, GPT-4.0, Blip, and Lava are the models that can give you that functionality, natural language description of your images. Then you have attribute tagging. So attribute tagging would be identifying objects or attributes in an image and then tag them with some kind of names or something, right? So that is another example of what you can do with image recognition. Then you have feature embeddings. So feature embeddings, remember we talked about embeddings to be the meaning that you give to things, basically. That's so when we talked about word embeddings, we're talking about the meanings that will be given to words, right? So in the same way, images can also have embeddings, which represent what the internal meaning or internal representation or idea that a neural network or any other machine learning model has for those pictures. So you can have a vector representation of those images for the purpose of searching. So just like you could use vector embeddings of words to search, do similarity search for words that have similar meanings. You can also do vector embeddings for images. And those embeddings you can do also similarity search for images that have similar content or similar meaning to the to that model. So those are some of the things you can do. So industry use cases for image recognition, you have retail where you can use it for product recognition. You can use it for shelf analysis. You can even use it for inventory, kind of where you want to see how we can identify things, right? So that's a good one of the good uses, product recognition, shelf analysis. Then security is another place where you can use this, right? With security, you can use it for motion detection, when people are moving around, especially in places where you have kind of um, you want to automate access control, right? And there can be any number of people that come in, right? So yeah, so with this, right, you can basically do security, motion detection, you can do anomaly detection. Anomaly detection is when you want to detect abnormal activity or abnormal events going on. So you can also use that. Manufacturer quality checks. This is another very good use for image recognition, where you can actually take pictures, as part of the manufacturing process and send those pictures to image recognizers that can identify defects and other kinds of problems in the items that are being manufactured. Then e-commerce image search, if you want to search for images of particular products or the kind of things that you want, you can essentially do that using image recognition as well. Then document classification before OCR, right? So you can use it to classify your documents even before you start your OCR. So that's a very good use for image recognition as well. Um, of course, when you do document classification, this is very useful for where maybe you want to write, you are building a service. Let's say you're building a service for an enterprise that has a lot of documents that are in hard copy or, yeah, hard copy documents. And we basically want to be able to scan them and encode them and make them very easy to access, right? So that would be a very good use case for that. Then you can even chunk them and make them part of a RAG so that it's easy for people to search. It becomes easily searchable. And then you can also, of course, before you chunk them, you have to use OCR to scan. So a whole pipeline of what you would do in that case would be um, classification of documents, scan first, classify after scanning, right? Then do OCR based on, the ones that maybe are in the list of the things that you want to digitize. And then after that, you can use them as part of a RAG so that they're easily searchable. So that's a whole pipeline of things that you can do. So in image recognition, one thing we have to understand is that when we say vision models or vision APIs, they are actually different from, um, you know, they are different from typical CV algorithms, right? Remember I talked about OpenCV. So OpenCV is, we're going to look at OpenCV shortly. Um, and we can try to run a few things with OpenCV. But when we talk about vision APIs like YOLO and all of these other ones we've talked about, they're actually different from OpenCV. So it's very, very important for us to understand that difference. And it's not going to be um, the same thing, right? I think they both have their own advantages and disadvantages. So CV is faster usually, but these days, these vision models are much better, right? And then the other thing to note is in enterprise settings, right? Most companies will prefer for you to use API-based recognition over deploying deep learning models, even though there's still the question of data, right? Where is my data going? Um, because when you use deep learning models um, for 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 image recognition, you are in a situation where you actually need a lot of compute. So it's a company ready to pay for that compute just for you to run digitization of their, large hard copy documents. That's a question to answer. Okay, so these are some of the things you can do using vision models. You have a vision transformer, right? What it does, a vision transformer does, it uses a transformer model. And what it does, is it takes images, it splits them into patches. A patch is basically a smaller sub-image of a larger image. And then it passes those patches through a transformer, and then the transformer is able to predict labels based on it. So this is how you can run it. You can see why we still use PIL in Python to manage the images, to manipulate the images, but we are using pipeline. Pipeline basically allows us to run um, models locally, right? So you would have to get the model locally, the VIT model. We can try some of these examples later on. Then you also can use the AI, the OpenAI Vision API, right? So in this case, you basically are calling GPT-40 mini, right? And then you are specifying the content, you specify the text, and then you also specify the image which you would have uploaded, and then you ask it to do recognition on it. It does that. So the OpenAI Vision understands complex scenes, it reads text, does basic OCR, it performs reasoning as well, relationships, counts, actions, and it can convert images to structured JSON. So you can actually give it an image and you prompt it to give you a structured JSON containing whatever you ask it to generate. Then capabilities, it can do captioning, it can do object descriptions, it can do scene analysis, it can reason about actions, right? You can ask it questions based on the image, and it can actually give you very interesting insights into it. You can also extract structured information from charts or documents. So one of the interesting things you could also do with this is give it an image of a table and ask it to extract the table. And then you can even ask it to give you the table as a CSV file. And then you can take that CSV file and process it. So that is a very powerful capability that some of these vision models have. Then after vision models, we also have what we call OCR, which is optical character recognition. So optical character recognition is basically a way for text that is embedded inside messages to be recognized, right? And where you can have such images could be in screenshots, in PDF files, in receipt, ID cards, forms, price labels, right? Now, some of the challenges that you have would be things like, handwriting. Handwriting, different people have different handwriting, and normally models that do OCR, on handwriting is normally a tough job because they there are so many different variants that different people will write, different ways that people will write the same characters. So this would be a challenge. But printed characters are easier for OCR to do because printed characters are kind of structured and are similar. So it's easier for them to scan those ones. The other challenge would be low quality scans, right? Scans that are not sharp. The other one will be slanted or curved text, which still points to handwriting, or maybe just text that is skewed because of how it was scanned or snapped. Then you have mixed fonts and font sizes, right, which could be a problem. You have poor lighting, and then you have, of course, non-English languages. So these are some of the challenges depending on how the OCR is developed. So how OCR works, the pipeline is basically pre-processing, which is normally done. The image is taken, the image is cleaned up, it is adjusted to a standard size so that the characters will have a standard size, and a bunch of other things are done. Then after that, text detection is done, which is to identify which parts of the image actually have text. And then when those parts of the image that have text have been identified, those sections of the image are then kind of cropped out and sent to the character recognition pipeline. The character recognition will recognize each character or maybe groups of characters. And then after that, once it recognizes it, will generate the corresponding character, either as ASCII code or just the character itself. And then we have post-processing. The post-processing, what that does is basically to try to clean up and identify things like typographical errors or misclassification or mixed recognition. And then after that, it's passed on to a structured output. So this is normally how it works. Popular tools that you will see for OCR, you see Tesseract. So this is widely used for, you know, OCR with in many different languages, right? Then you have Google Vision OCR, which is very accurate, but it's cloud-based. You have to call the Google Cloud API. Then you have AWS Textract, which is also excellent for form extraction and table extraction. Then you have Paddle OCR, which is very lightweight and fast. Then, yeah, so this is how you could use Tesseract, right? With Tesseract, you just import Tesseract. You open the image that has the, you know, the text that you want to recognize or do recognition on, and then you just extract the text with image to string. That's all. It's as simple as that, image to string, and then you can print it. So that's what Python does. You can also do advanced OCR with structured output by calling image to data on it, right? And then it gives you that. Then if you want to improve accuracy, you can use the CV library to do a bit of pre-processing. So some of the pre-processing, like this first one, is you are converting color to gray because a lot of these libraries are better able to do recognition on grayscale or black and white, right? Well, black and white is not really that good because with black and white, you lose some kind of information. But with grayscale, you are able to keep all of them in one color and it's easy to recognize, right? Colors sometimes may be difficult to recognize because some colors may be so bright you can't distinguish it from the background, or you can mix up things. So that's why you do a bit of pre-processing. You use this CV2. CV2 is an image library for computer vision, basically. That's why it's called CV, and it has a lot of different functionalities, different utilities that allow you to do stuff. So this CVT color is one of the things that you can use to do color conversion, right? So you're basically converting the image to what we call grayscale. So you are doing color BGR is blue, green, red, RGB basically to grayscale. So you convert the image to grayscale and it gives you an image in grayscale. Then this other one is using a threshold to convert the grayscale to a black and white image. So you're essentially using a threshold binary. Um, and these are additional flags when you're doing that. So this is just an example of how you convert a grayscale image to a black and white image. Then you can then take that black and white image and put it in the Tesseract image to string. You're likely going to get higher accuracy because of the pre-processing that you have done with this CV2. So that's it. We have a bunch of other things. You have LLMs, that can do this for you as well, multimodal LLMs. So you don't need to, you pass them in. So typically, you can pass like a GPT 4.0, for example. You pass it content as part of your prompt, but remember you have to specify that it is an image URL, and it's going to be able to take that image and then extract the text from it. So these are some of the things that LLMs can do, right? In terms of OCR, they can extract key value pairs from your scanned document or your screenshot, name, total amount, invoice number. It can extract entire tables, from it. It can also do layout analysis, basically separating paragraphs from sections, headers, and so on. And then it can also do visual and semantic extraction. So you can actually prompt with things like find the expiry date on this product label, and it does that. Identify all numerical values and units. So these are more advanced OCR that you can do with LLMs. So we'll just end this with this last one where you can talk about multimodal workflows. So when we say multimodal workflows, what do we mean? What are the things that you can essentially do with your multimodal models? So one example is image to text to speech, which is very interesting. You can take a scan image and generate a narrative for that image and then pass that narrative into a text to speech synthesis. So it speaks out, a description of the image. Another one is text to image to explanation. So you can take a text and you can generate image and then do explanation. So this one is nice for where you can generate a UI mockup and then or diagrams and then narrates them. Then you have audio to text to image. So you can have audio that comes in. You have a speech to text that will convert that audio to text, and then um, you can then generate images based on that text. So what this does is dictation. You can ask someone to describe an image, and then you generate an image based on the person's description. Then you have image as well as text with semantic search. So this is very nice for like if you have a library of images or pictures and you want to be able to do search, right? This is one thing I've always wanted to do, and I might even consider building an app around it. Is I have a lot of images in my image library on my phone, for example. And I've always wanted to like search for an image that I snapped with my family or with my wife or with my mom, or a particular event that happened and I snapped the image and I'm looking for that image. So instead of scanning for it, right, couldn't I do semantic search? So that would mean I would first of all need to um, do embeddings of those images first. So you can take the images, get embeddings, store the embeddings. Now, in a multimodal, if you mix the image with text, that's where you have to combine it with text because when you are taking the image, you can first of all caption the image. So you pass the image through an image to text that will generate a caption for that image. Then you can store the embedding of the image along with the embedding of the text. So if I now want to find images that match a particular caption, then when I speak, I say, okay, I want an image that I took during my TM that happened so and so. I would then use same as a RAG workflow, right? I would then use um first of all a text embedder to embed that description, that question I asked into an embedding, a vector, and then I can search in the vector database for a similar caption, right, based on embedding semantic search. And then when I pull that up, remember when I stored it, I had also stored both the embedding of the caption and the embedding of the image. Then I can retrieve that image that was stored along with that caption, along with similar images that are similar to the embedding of the image. So that's a very powerful app idea. You know, I could, I'm giving everyone ideas. So these are some of the things that you can do with all of this AI. Yeah, real world examples, visual meeting notes, so slides and audio, you summarize it, dashboard screenshot, structured. So you can take a screenshot of a dashboard, like maybe you want to do a report. So it can generate a structured JSON, right, of a report. One thing I've actually done recently is somebody told me, oh, do this web landing page for me, right? And I told him, give me a screenshot, and they gave me a screenshot. And I put that screenshot in was it ChatGPT or either ChatGPT or Claude, and I said generate HTML and CSS using Tailwind, and they actually did that, and I was amazed. I really didn't need to do much else. In fact, you can even tell it, okay, generate it, turn it into React component, and it will do that for you. So these LLMs are very, very powerful. Then product image description. And from a product image, you generate a description. From description, you pull out a search engine optimization parameters or metadata. And basically, that is kind of in an e-commerce application, for example, when you tell people upload an image of your product, you can generate SEO metadata straight up from the image that they upload. So you now have improved search engine optimization for that site. Then an app that reads street signs aloud. Well, Google has done that already, but you can still do yours. So these are some of the things that you can do with all of these. Just being able to um, you know, um, harness all of that power, right? So multimodal LLMs will simplify your pipelines because you don't need to stitch multiple machine learning models manually. You can basically give it in one mode and it gives you an output in the other mode. So for example, you can take a photo of your classroom notes and you get a summarized audio file, right? Immediately. So that's the power of multimodal. So yeah, so this is a hands-on we can do, where you take an image, you do OCR, you do summary, and you do audio output. But I'm going to go back just to complete the hands-on, and we will go again and try to do the image generation thing, where we had a bit of challenge because the APIs that I was using were old APIs, and they were just giving me all kinds of errors. So we are going to try again. So first thing is, um, I've been able to find um, a free, let's start with Hugging Face. I've been able to find a free model that we can use with Hugging Face. So let's see, give me a second. Um, I actually remember that if you recall, we actually did a bit of this previously. It's just I forgot the name of the model that we used when we were doing that. So when we were doing um, image generation, we were using Black Forest Labs Flux One. I totally forgot. So that's what we will use. So we are still going to use the Hugging Face inference client, right? And when we call inference client, the provider was replicate. And of course, we are still using the Hugging Face API key here to call it, right? The provider is replicate. And we are still going to call client.text to image, which is the correct thing to do. But I was struggling to find a very good um, model. So let's run this now. Okay, of course, after generating it, we need to save it so that we will be able to see the image. So we just call image.save and we specify the file name. So we can say, let's just say test image, right? And it's always going to be a PNG file. So test image.png. Okay, so I can now open test image, right? So a few things, right? I want to try now. In the context of the prompt itself, I want to dwell a bit more on the prompt. And rather than it doesn't really matter what model we are using or whatever, but what I wanted to kind of, you know, um, talk about and let's just dwell on a little bit was how some of the parameters that we would supply when we are generating this image, how they can affect the quality. So let's start off with prompts that, when we're talking about prompts, remember we said there are three things that you have to look at. The first one is content, style, and composition, right? Content, style, and composition. So in this case, for example, we said astronaut riding a horse. We didn't give it anything else. So it just gives us stuff and it does its own composition. But now let us add a little bit of style, right? So you can say watercolor paint, watercolor painting, right? This is just me changing the style. I'm going to rerun this again, but this time of course, it has done a new image, so I'm going to update the image. Now, because I asked for watercolor painting, you can see how the style has changed. The other one was realistic. So if I say realistic, right, it's going to still try to give me a more realistic image, right, which is similar to what it gave me before. But the very fact that I have said realistic now means that it will try to do something that matches realism. Okay. Now, I could say realistic, we can say sunset background at the beach. Okay, so I now add composition, additional composition stuff. So I am now telling it, giving more specific stuff, right? If I open this one now, is you can see sunset background at the beach. We could say sunset background on the mountains. So again, um yeah, so let's see how that looks like. Okay, so it's kind of interesting. Now, so remember we said there were other things you could do. For example, you can you can specify negative, right? You can specify negative prompt. You can so let's start off by putting some of those in. So this is a prompt, right? So this is the prompt. Now, if we want to add a negative prompt, we can say negative prompt. Then we specify the negative prompt. So in this case, let's say the negative prompt, I want it to be blurry. That means I don't want it to be blurry actually, right? Blurry and oversaturated and dark. So I don't want it to be blurry. I don't want it to be oversaturated, and I don't want it to be dark. So that's negative prompt. So let me run that now and you see what you get. So because I said I don't want it to be dark, you can see it's now giving me, um, you know, um, better lighting, right? It's still mountains though, right? Good. So now the next thing we wanted to try was guidance scale. So guidance scale, we can say guidance scale. Let's try, we start with guidance scale of 9, which means 9 is a high value, means um, do more of what I want than what you want, right? So that's guidance scale of 9. So I'm going to open that. Okay, now let's go back and give a much higher guidance scale of 12. And okay, now if I reduce the guidance scale to something like 6, guidance scale is normally from 7 to 12. Okay, so let's say 7, right? Um, okay, so let me see. I hope I did not exceed my, yeah, I think I may have exceeded my, I think I may have exceeded my, you know, yeah. So, but anyway, I think I just end there. I just wanted to show some of these parameters, how you can change it. So I would, I would, I would recommend go and try it out and see, um, what you can get. It's very interesting what you can do. But remember, when it comes to prompts for images, you can get vastly different images just for very simple um, you know, um, changes in your prompt. So if you dig deeper into the documentation, you will also be able to see a lot of stuff on um, Gemini. Gemini actually, it's a bit complicated, so we don't have enough time to go into that. I've just found that, well, Gemini Flash image um, is not easily accessible, so I can't immediately find a model from Google that allows or that has image. This one is there, but I'm surprised because I actually have a payment plan, but it's telling me I have exceeded my quota. So unfortunately, I don't have time to solve that problem now. But it's something that, you can go try out. Okay, so let's now look a little bit at um, just a few moments. Let's look at image recognition and what you can do with CV. You can do a lot of stuff with CV. So without having to run it locally, I don't want to run it locally. I hope we will not be in that situation. We'll have to run it locally. But we can use PyTesseract. So let's use PyTesseract. So so first of all, you do import PyTesseract and we import PIL as well. PIL is for image manipulation. So anytime you have to manipulate images in Python, PIL is the thing, right? And um, most other SDKs or libraries or programming languages or frameworks will have that, right? Will have that. So whether it is, I need to install PyTesseract. So whether you are using JavaScript, Node.js, whether you're using you know, Flutter on any of the iOS or Android or anywhere, right? If you check the documentation, you will see how you can install any of those things, right? So we get that. So typically you will just import an image using the image class. You open an image, right? And so I need to upload an image here. So what I will do is, let me see if I can quickly bring one of this test image which I had done. I'm going to download it and then re-upload it into the other environment. So let me load. If I can remember the name, I think the name um, the name is test image. So let me see if I can find that test image. Okay. So test image is uploaded. So this is the image that was generated. So I now want to do a little bit of just extracting. Okay, so this is not an OCR, by the way. This is an image. I can't do OCR on this. So I need to find an image I can do OCR on. I was going to try out image recognition, but let's do OCR image to string. I may even try Tesseract. Let me see what PyTesseract actually gives me with this test image. It's good to try it out. Let's see. So we create a new image, then we just pass it into the PyTesseract and call image to string, and then let's see what we get. So yeah, there is no text here. So there's no text here. Um, right. So let me go look for a screenshot that has some text in it, and we will. So I'm going to upload. So to upload again, I right click, and I pick upload. It's going to open my um, Explorer where I will upload. So I have this, yeah, so let's see. This is just a screenshot I got, when I was installing something. And this is it. I don't know if you can see what is here, but there's some text here, right? I was installing some software, so I took a screenshot. So let's see how PyTesseract does that. This is a very long file name, so I'm going to just rename it to screenshot. Okay, so I will open screenshot, right? And it's JPG, sorry, JPG, not PNG. Okay, so let's run this. So this is PyTesseract, and let's compare what it has recognized. It is almost like you can see SSH client slash n. If you are using SSH client to connect to other Git repositories, select what SSH client to use. So you can see it's almost a perfect job. You can change it later in the preferences. Use system SSH client. So this is like image to string, but you can even do a full thing like structured this thing by calling pytesseract.image to data. It has that image to data function, right? And you can now you specify the image, right? IMG. Then you also specify the format that you want the data, and you can choose any number of different formats. It actually output type. So this output.dict is going to give you a dictionary, right? So um, let's call it data. And let's see how this one works. So it's basically going to generate a dictionary. And well, it kind of it's recognized a bunch of stuff, right? Level one, two, all of this. So of course, in this case, maybe I don't need a data structure because what I had there is not a data structure per se, it's actually a sentence. But it does pick all of these sentences, and what you have is a list of the words that make up the sentence. So PyTesseract is very powerful. There are a bunch of other ones as well. Um, so many other things you can do. Um, we can't go through all of them, but I would say go try out and see what you can do with, you know, image with OCR. Now let's look at a little bit of image recognition. Um, so, well, you can run Vite in here. Let's see if we can do that. We have a bunch of models in Hugging Face um, that you can use for image to text. For example, image to text will give you, okay, there's NVIDIA Nemotron OCR V1. So you can use this for OCR as well. I don't know if this is available, but we can try it. So let's try this. So to access NVIDIA, of course, you use the OpenAI client. So we import OpenAI first. From OpenAI, import OpenAI. Then we now make a client OpenAI, and then we specify the API key is os.get environment. The API key we'll use is okay, I need to create a new .m file here because I didn't. It's a new project. So I'm going to do that now. I just pasted this here, but let's call it open router API key. So that's the API key. I also need to specify the base URL. So base URL is I don't have a .env, so I'm just going to type that one in here. So it's https open router dot AI API v1. Okay. I don't know if there is a model, default model. Let's see. Um, there's a provision for default model, but okay, so we don't have that here. I have to do it later on. Okay. Um, hold up. I don't know if I can do that with the regular um I don't know if I can do that with okay, this requires I need to pull the model in. So this still will not work with an API call. So I think I'll leave that. There will be a time when we'll actually look at how we can run models locally. But yeah, Nemotron, it would have been interesting to try this, but I'm just seeing that there is no API option for us to try out. So yeah, there's no API option. We still have to download it and run it. You even have to pull it from their um, repo. Okay. So, but there are a lot of options, and what I would just want to say is try different things. The last thing I want to do is just um, um, captioning, right? So let's see if we can do that using the same Hugging Face. So we use Hugging Face already. So I'm going to see if we can use Hugging Face to do that. I should be able to call on the okay. Oh yeah, I think I finally found how we can do um image with um so let's do that. Let's do image not image generation but image recognition um using Gen AI. So let me take this out. So image generation with Gen AI. So again import Google the generative AI as Gen AI. Um, I think it should be Google.generative AI. Okay, so we have that in. Then we need to set we need to configure the API key as usual. So to configure, you do gen AI dot configure and we'll specify API key is equals to os.get env. We'll specify Gemini API key. I need to also import os and .env and load.env. So hopefully it loads.env. Load.env tells me false. I don't know why. Okay, because there is nothing in my .env file. So let me copy and paste the .env values. Okay, so if I run .env again, it's going to give me true. So I then configure Gen AI. Okay, so now that I've configured Gen AI, I can now look for a model. So let's look for Gemini flashlight latest. So we can use model equals gen AI dot generative model Gemini flashlight latest. Okay. I hope this one is multimodal, right? And we'll be able to um, handle images. So let me open the file. So I'm going to open the file. The file is test image .png. Yeah, PNG. I open it for read. It's a binary file, and I read it into the image. Okay. I also need to import base 64 because of the encoding. So I'm going to need to import base 64. So I open this file and I read it into the image variable. So now I have the generative Gemini flashlight. Oops, there's a typo here. So let me do this again. Gemini flash light. Gemini flashlight. Gemini flash light latest. Okay, so I can now um, send a prompt, right? So in the context of Gemini, because it's basically a um, um, a multimodal model, I'm going to ask it to generate content, not generate text. And then I'm going to specify the prompt. So I also need to pass in everything. So first of all, I will pass this in and say this is inline data. So the inline data is to specify that I am passing in additional data, right? And that additional data is the image, right? So image, right? So this is the image that I have read. Um, I actually need to decode the image. So that's where we use base 64, base 64 dot b64 encode. We encode the image, then we decode it, but not as UTF-8. Well, I don't know, it doesn't have to be UTF-8. Maybe that's okay, but I don't want to do that. Then we specify the name of the image, and then we can also specify the MIME type. MIME type. MIME type. The MIME type is image PNG. So this is the first information I'm sending. This is basically equivalent to you uploading. If you were chatting with Gemini on a chat interface and you uploaded the image, this is equivalent of doing it, right? You send it in this data structure that says inline data, and then the value of the inline data is another data structure that says the data, and you base 64 encode the image that you have read. You read it as a binary file, right? Then you base 64 encode it, and then you decode. Decode means you decode it into a um a character string, basically. That's what will be uploaded as a base 64 string. Then you pass additional information like the name of the file, image.png, and the MIME type, which is image slash PNG. So that's the first thing. Then the second thing is the actual prompt, which is you can pass it in as text, right? Or something. So in this case now, I will pass in the prompt just as a simple text and say, okay, write a a um an appropriate caption describing the attached image, right? So I just pass that in. Okay. So then this should run. Okay, yes, I shouldn't have put the name. So let's skip that. So this runs, so since Gemini Flashlight Latest is a multimodal model, it is able to take this image and act on it based on these prompts that I gave to it. and I get a response. I can then display this response. So let me display this response as a markdown so that it will be easy for us to see. So from IPython import display and markdown. So this markdown is just a way to help me display this thing in oh, hold on. I think I didn't get this very well. It should be IPython display, import display and markdown. So display and then markdown and response dot text, right? So when we run this, you can now see this is how Gemini's flashlight is able to do the image recognition. Here are a few captions, so it gives different options, witty and humorous. So this is where the power of multimodal large language models are. I can then even interact with it, right? Like the image is there, right? So I can even just tell it something like identify the number of um, objects in this image. Identify the number of objects in this image. Um, return uh, um, I need the results in a JSON array format. See, that's the beauty of large language models now. I can even tell it how it should give me the results, right? And then if I run this, you see, you get this label, astronaut box. It even gives me the box dimensions. Can you see this? Label horse, box 3D, label saddle, box 3D. So it now becomes a very solid um, image recognition, object detection. You can basically do everything with these models. So I'm going to end the class there at this point. Thank you very much for paying attention.